So yeah, my name is Al-Attiyah and I'm from Imagimob, and today we'll be talking about machine learning for condition monitoring and fault detection. So at the beginning, I'll talk a bit about myself and then a bit about Imagimob and what we do. And then we have prepared two use cases for application of machine learning to different kinds of machines in the field and in research. So yeah, I'm the head of projects and customers at Imagimob. So what we do is that we work closely with customers and help them either bring machine learning or AI into their products. And this is done using our tools or we take over the projects for them. So we have experience working from a wide variety of projects, some of which have gone on to become products. And so we have experience with end-to-end edge machine learning. And what we mean by end-to-end is that we do the whole chain of the development. So we plan the data collection and we actually collect the data. Then we perform the analysis and the model building. So getting to understand the problem and how to solve it. And then eventually we actually deploy these models onto edge devices. So normally microcontrollers, and the most common one that we work with is the ARM-M4. So we work with demos, proof of concepts, and actual products. And a bit about my background. So I did my master in electric power engineering at KTH, and I did a thesis in acid microgrids, and my bachelor was in electrical engineering. And this is in University of Newcastle in Australia. So, but now I mainly work with machine learning and AI rather than with electrical engineering. So before I start to talk about Imagimob, the first thing we have to discuss is what is cloud AI versus edge AI. So normally when we talk about AI, we're talking about data being sent up to the cloud, and then you build models and perform computations, and then you get some results back. And this means that you have no real limitation in terms of processing power, because you can have big computers running all the computations. But our focus is actually on edge AI, which means that we work with devices close to the source of the data. And this means that you have very little latency. So you get the computations quickly and you can perform seamless actions. But with that comes the problems of the fact that there's constraints in terms of power consumption. So you want your device to last a long time rather than die very quickly. And you also have limitations in terms of processing power and the amount of memory that you can use on the device. So most of the time we work with models that are less than 20 kilobytes and typically less than 15 even. So what Imagimob does is that we have our development platform, which is called Imagimob AI, and that lets you streamline the model building process. So it allows you to collect high quality data and to be able to annotate them very quickly. And it also allows you to kind of visualize the data and combine it with the other forms of data. So you can have your machine signals combined with the video or audio data so that you can get an understanding of what's happening in the real world and what your data is actually reflecting. And then you get tools to be able to better understand how much data you have, which gives you a better understanding of if you're in a good state to actually start the model building or if you need to collect more data. And then you can actually build and train models very easily. And then you evaluate them. And finally, you can very easily deploy these models. So you can optimize your built models for edge devices. And the output is simply raw C code that you can deploy on any device that can run that. So yeah, it allows engineers to be able to develop models very quickly, and it reduces time to market and increases productivity. So you can get prototypes out very fast and then eventually go into products. So these are some of the applications that we've been working on, and they demonstrate different kinds of sensors that we've been working with. So we have been working with the Acroneo and OSM on these earbuds, and these allow you to control your earbuds using just hand gestures. And this seems like a novelty at the beginning, but with earbuds, you don't actually have room to be able to insert functional buttons. So there's no room to have buttons. So by using a radar and gestures, you can actually get a lot of flexibility with what you can do in terms of controlling them. And in this case, we are focusing on radar data. We've also worked with automotive and then manufacturing machinery. Also worked with the safety companies. So this is the Scania's One Home safety vest, which can detect enters and exits from a truck and if a person has fallen. We've also worked with the power tools, where you actually get the machine data and can actually classify what the machine is doing based on some basic information. Then we worked with agriculture and machines, as we will go into in this presentation, and some fall detection in a classical watch. So this is a bit more about our use cases. We work with a wide array of sensors and different kinds of machine learning and AI. And our main focus is on edge AI using deep learning. So yeah, about the use cases, today I'll be presenting two use cases. One is a project. It's a Vinova project called Spice Drives. And there we have condition monitoring. We built supervised learning models, and the specific model is a regression model. And in this case, we already know what the data reflects in real life. So that's why we chose these type of models. And so based on the input from this regression model, we expect to get a grade that reflects the condition of the machine. And in the second use case, we have an actual customer product, and it's classified. So I can't go into too much detail on the specifics, but I hope that I can convey enough to show how interesting it can be. So here we talk about the fault detection on an actual product. And since it's actually very hard to get data where the machine has broken down, we chose the anomaly detection route, where we can use semi-supervised. And what that means is that most of our data is unlabeled, but we have some few samples of labeled data where we can use to tune and validate the model to make sure it's running optimally. So in this anomaly detection, we use some autoencoders to be able to reconstruct the input, and we use the model to identify deviations from normal behavior. So when you get sufficient deviation, then you can flag it as an anomaly. So yeah, let's go into the Spice Drives project. So the Spice part refers to self-predicting and intercommunicating electric, and then it's a drive. So it's a Vinova project that we're running with the KTH, ABB, Lumen Radio, and Ericsson, and it's a classical case of predictive maintenance. So in this project, KTH has created a testbed where they perform accelerated aging on a machine. And the idea is that you take a machine that's completely healthy and age it in what was supposed to be 10 days, all the way to breaking. So then we have kind of the entire timeline of the machine from healthy to broken in terms of data. And while performing this test, the data that was collected is low frequency, where we have 4 kilohertz, and then high frequency at 64 megahertz, and also a temperature. We chose to focus on low frequency, and I will, yeah. So the low frequency was prioritized because it's the easiest to obtain from a product point of view, and as we understood it, it's also very difficult for humans to be able to identify the current condition of the product based on the low frequency data, which makes it ideal for something to try to tackle with machine learning. Yeah, so how the aging process was done is that every day for 8 hours, the machine was heated beyond its rated capacity. So I think the machine was rated for 80 degrees, and then it was raised to about 222 degrees. So the idea was that after 10 days it would break down, and we did actually have a breakdown after 12 days. And then we used the regression model to try to track this condition. So this is a picture of the actual test setup. I'm not an expert in machines, so I can't identify all the parts. But all I know is that we had a machine with a locked rotor for safety reasons, and it was run beyond its temperature rating. So regarding the problem that we approached, so we had the data that was three-phase voltage and current, and this data was sampled at 4 kilohertz. And then we have the problem that we were trying to solve is that we tried to map out the degradation profile of this machine. And since we had an even distribution of healthy and unhealthy data, we chose to approach this using supervised learning, and hence we decided to use regression models. So in terms of actually labeling the data, what we did was that we split it up into 4 different categories. So we have 0, which is healthy, and then we have 0.3. So the first quarter of the data was labeled as 0, the second quarter was labeled as 0.3, and then we have 0.6 and 1. So the idea is that you gradually evolve from 0 to 1. And then in terms of this specific data set, we split it up into 60, 20, 20. So we use 60% of the data to actually train the model, and then we use 20% to perform the validation and tuning. And finally, the last 20% is data that the model hasn't seen before. And here I have a video of the different properties. So the first thing is this is the input data that we eventually use. So here we can see clearly that it's a three-phase sinusoidal function. And we can see here that it's the current and the voltage. So the smaller values are the current, and then the higher ones are the voltage. And this is the view inside of our tool. And if we had a video or some kind of audio, we could actually play through it. But in this case, we don't. But we already knew beforehand what the data was. So that's not so relevant. And here we see the high frequency data and how it looks like. So yeah, as I said before, we didn't actually use this for the model building at this stage. We mainly used the low frequency. And then here is the actual output of the model. So for the given input sinusoidal functions, we get this output measurement, and the model is trying to predict the condition. So in this graph, we can see a number of very interesting characteristics. One is that the model was able to correctly identify a gradual trend from semi-healthy all the way to broken. One thing that we can clearly see is that the model jumps from 0 to 0.5 abruptly. And well, we believe that at this stage, the model was actually running at its rated temperature. And then it jumped up to, this is when we actually perform the aging cycles. The other thing that could be clearly seen is that there are peaks and then the model output stabilizes. And you can actually connect these peaks to the number of days. So here we can see that there are 12 peaks, and that correlates to the 12 days that the machine was, or the 12 cycles of the aging process. So one thing that could be done at the next stage is to actually allow the machine to stabilize before sampling the data so that you get a smoother curve. But yeah, regardless of all these points, you can clearly see a trend going from low, from healthy condition all the way to degraded condition. And at this last point, that's actually when the machine breaks down. So you have a breakdown in the winding, and then the machine is no longer able to run. Yeah, so this is actually what we did for the model building. So we have some very basic processing. We have an input of size 6, which is the 3 phases of voltage and 3 phases of current. This is passed to a sliding window, and then we perform a very simple Fourier transform. And then this output of the preprocessor is then passed to this network, this neural network. And you can see that it's composed of different layers. So we can see that there's some convolutional layers, some LSTM, and some dense layers. So yeah, and this model was selected through our auto ML functionality that I will talk about later, and same with the processing. And now what we will demonstrate is how easy it is to actually deploy this or to go to actual C code. So with the click of a button, we actually generated some C code that could be deployed straight away to a microcontroller. And we can see here that the actual size of the model is very small. So in terms of RAM, the model is 6.9 kilobytes, which is quite small. And then in terms of flash, it's even smaller at 3.6. And then you get some information about what the model is composed of. So just to summarize, we had these inputs for the model. We chose the low frequency sinusoidal function, and then we got this output condition plot. So yeah, just to conclude about this space project, it was able to successfully track the performance or the condition of the machine. And it was able to do what would otherwise be very difficult for humans to be able to detect. And in terms of usage, how this would be applied to real life scenarios, that you could apply thresholds at certain points so that you can get alerts for operators to be able to move out to the field and apply the necessary fixes. And it could be to perform maintenance so that you can bring the condition back to a safer level, or replacement of the machine so that you catch the problem before you stop operations or have some problems. So this model was actually built using one machine, and the next steps would be to include more data and see how this performance generalizes. And then once you have data from a second machine, you could then deploy it on a third one and see how it works. So now we've looked at condition monitoring. What we'll look at now is fault detection using this customer project. And what's interesting in this customer project is that we took a little amount of data from one system and we were able to have it generalized well to many other systems. So in this case, we have as our data input, we took the power of the product and the output level of this product. And what we saw is that the data is highly variant. So you had different systems rated at different capacities. The other thing is that since this is an actual product, you obviously can't break it. So we had predominantly healthy data, and we decided to approach this from an anomaly detection point of view, where you can use a lot of data to train normal behavior and have the model try to identify abnormal behavior. So here we trained the model on 1 day of data, and we tested it over months of data from other systems. And here are some plots of kind of the model. This first one identifies, it shows the model trying to reconstruct the signal. So how it works with an autoencoder is that the model learns to reconstruct the signal. And if you have a deviation from normal behavior, then the error in this reconstruction will become very large and you can detect it as an anomaly. And here we can show how you can identify anomalies in a data set. And you can see here that there are actually a lot of anomalies detected. So that's why we move on to the next level where we set even harsher thresholds. So this kind of demonstrates how you can fine tune your threshold to be able to kind of choose how, what kind of anomalies you want to detect. So you could have, for example, here is just a warning. Here you can have just anomalies that might not be critical, and you can also identify critical anomalies. And this gives more power to the operator to understand what's going on with the product. So the conclusion in this case is that an anomaly detection model was able to be created for situations where you have a lot of normal behavior data and you have few samples of abnormal behavior. And the main reason to have some few samples of abnormal behavior is that you want to fine tune your model and actually verify that it's working correctly. Because in this case, you could have a model that never triggers, and that's fine and all, but you want it to trigger sometimes. You want it to trigger when you have a problem, to be specific. So yeah, I've kind of gone over how you can use it. You can have different levels of severity of different anomalies that you can have different reaction plans to. So the operator has more power. And this can help to identify major problems before they get severe enough to stop operations. And this can lead to increased efficiency, longer lifetime, and reducing costs. And for the next steps for this model, you could actually deploy it onto a real product and evaluate the performance. You can also create a feedback loop where you identify the anomalies and then you go back to verify if those are indeed correct or not and continuously improve the model further and further. So yeah, to conclude the bit, you can use different kinds of machine learning models and algorithms to different kinds of electric products, and you can use the different systems to be able to kind of approach problems from different ways. So we saw how you can use a regression model to track conditions and an anomaly detection to identify faults in the system. So to summarize a bit about how you can use Imagimob AI and why it's useful for these kind of projects, and these are the big three points. One is that you can, by having a ready-to-go visualization, you get you can see clearly what's going on with your data, and you can easily apply labeling to it. We also have very simplified machine learning. So you have an auto ML, so it allows you to build models with zero code. So you're ready to go straight away. This means that as soon as you collect data, you can put it in, label it, use the auto ML to generate some models, and then you can assess how it performs. And then if you want to squeeze out extra performance, then you have the pre-processing ready to go. And then finally, if you want to actually test it out on a product, we saw that it's just a simple click of a button to get some C code, and you can put that on a machine and see how it performs. So this leads to more rapid prototyping, better models, and you get better edge AI. So yeah, thank you for listening to my presentation.
Thank you, Sam. This was very, very interesting. I'm wondering, are there any questions from the audience? Absolutely. Barry, please go ahead.
Yeah, thank you, Sam, for the interesting presentation. What is your experience in terms of regression models that you applied? Was linear regression models, learning linear regression models sufficient in most of the applications? Or in this case, you applied nonlinearity and non-Gaussianity? Also, for the neural networks, I assume maybe you are using backpropagation. Am I right? Or something else? Thank you.
Yeah. So yeah, we are using backpropagation, and I'm not exactly sure what type of regression model, but I think it's non-linear because, as we saw, it has a lot of different layers that goes in. So it's not a traditional sense of a model. It's more of a combination of different kinds of deep learning layers that you can use together in the model.
Okay. All right. Thank you.
Any more questions? What would you say, Sam, is the hardest, so to say? Is it to evaluate? I mean, to do condition monitoring, something you can do probably regularly, or is it to detect the fault before it happens? So can you combine these two in a smart way?
Yeah, you can definitely combine the two because you can see from the condition that when the machine is operating abnormally, this will also show up in the regression model. The main difference of the two systems is kind of how you formulate your problem, and that's for the condition monitoring and for the anomaly detection. The big problem is data, and I think that's always the big thing, because you can always, once you have the data, you can always analyze it and process it and build some machine learning and have it follow what you tell it is the right way to work. But actually getting the data and understanding, is this data supposed to be healthy or unhealthy, that's where the limitations are. And in this case, so Luke has also been working on this project, and luckily we've been able to see the entire timeline of a machine. So we actually went from healthy all the way to broken, and you know that halfway it should be halfway through the condition, or if it's exponential, then you can you have some idea of where it is. But if you would go to the field and try to pick a machine out of there, you don't know how long this machine is or where it is in its condition profile, and that makes it a bit more difficult.
That was my point. Can you make condition monitoring assessment without knowing how the broken machine express itself? That's
yeah, and then I think it's that's where the anomaly detection kind of takes over, which is if you really understand how the healthy behavior is, and you can get that data easily because when the machines are first manufactured, you can collect data from thousands of different machines and train a robust model, and then you can track the deviation from the standard behavior and apply some logic to the output of these models.
Mm.
I can add a few things here. I think what is important now is that we understood that we can use the methods that Sam has presented to evaluate the aging, which was not clear to us. We are used to revert to our own electrical engineering background when we analyze, for example, the impedances, positive, negative sequences, and or other aspects, more classic aspects, I would say. But then when you use a completely different approach based on the knowledge that Sam and his company has, then we wanted to understand whether you can see something that we don't see. And there is something there in the data that we, with the classic methods, we cannot find. That is what we can say from what Sam and his team has done. Now, the problem of reproducibility of these results is, of course, on the table. So you need to have many machines, many machine cases. Like we are looking now to the second prototype, which is still under the killing process after 28 days. So you can have machines that are behaving slightly differently. And all of these things come into the picture when you make this massive collection of data that then are going to tune the models that Sam was talking about. I think the step again here is, to me, that we can see something. And this is, for me, the starting point for something else, for the next steps. So we can see, based on what Sam has shown, that the models are even not very computationally intensive. So we are getting closer and closer to the possibilities of embedding these models into existing drive system control boards, which many years ago we would not even have thought about. So these are all small steps towards the goal, which for me is to implement let's say, the concept of edge computing into an electric drive system. And then we can talk about all the different cases and how much we can cover. But I think it is important to see this perspective. This is a long-term perspective that has a lot of opportunities.
And the thing is, we can slowly get more and more data, and over time, these models will get better and better until you actually have like a stable data set that you can put on a drive, and it can generalize well to other machines without needing any further input.
Exactly. That was my next question. I understand from what you presented here that you're using the 3-phase voltages and currents, right? And some temperature, probably. I'm
not on the model, just the 3-phase currents and voltages.
Exactly. And would it be possible then to, for example, as you say, as more and more data is available from different machines operating in different countries at different temperatures and pressures and so on, to include further variables into the detection algorithm? Would that make it more robust?
Yeah, I mean, with more variables and features, you have more information for the model to make a more informed decisions. But also, if you make your model bigger, you also need more data to be able to tune it properly. So, and one thing is that if you have a model that works well on currents and voltages, then why try to add other stuff that might that the model doesn't really need? So we usually kind of expand the scope of the model as we see that it starts to struggle. So if, for example, there's a specific case where you can't get the model to work, then we will see, okay, including the temperature or the high frequency data, does that give more information to the model to make a more informed decision?
I was more thinking like exactly that. If you train this for with data, currents and voltages that you're that you obtained in Sweden, and suddenly you move to, say, South Africa, where you have probably 10 to 15 degrees more on average temperature, which will change, I don't know, the resistivity of copper, for example, or whatever. If that, for example, could make, it would be, I see it as a mixture of these cloud AI and edge AI. So you take information from many different similar machines, but in different parts of the world. But then you take that information and implement it in your own little model, so to say.
Yeah, and that's definitely something you can do. And there's two approaches to that. One is that you can let the model learn the relationship between the currents and the temperatures. But one other way that we found very useful when you are limited in terms of data is to help the model by actually apply these relationships yourself, so you scale the values accordingly. Because you already know what's the what deviation in current consumption you're going to have due to the temperature. You can process that to kind of scale it accordingly, and then the model doesn't need to learn that. So it's a bit less for the model to learn. I can just focus on the more important stuff.
That's interesting.
So when you have an infinite amount of data and an infinite amount of time, of course, the models will learn everything that you needed to learn. It will be able to reproduce the physical phenomena precisely. But when you're limited in terms of data, then you try to see, okay, how much can my model learn and how much can I do instead of my model that could be easy to help it get going?
Yes. Some of them are parameter sensitivity, some of them are state. And we need to make a distinction between those. And if there's a model and then there's a parameter sensitivity, not necessarily all the parameters of the model are going to impact to improve the results. And for the case of state, then there's a supervised learning that you mentioned. Some of these algorithms actually go 40, 50 years back. And they have been around. And the reason that they are now successful is because we have the practicalities in terms of computation. And that is going to be also data quality. If wrong data is fed and there's no data quality, then there's not going to be improvement in the results, but there's also algorithms to adjust that. Just wanted to put a small note there on that. Thank you.
And that is the reason why we use the less sensors as possible and the more reliable ones, which are the current sensors within the drive. If you cannot rely on those, everything will just disappear in the power electronic system. So that's the minimum we can do, and that's what we fixed as a requirement for Sam and his team. We're going to use those and nothing else. If you succeed to use those to detect the aging, then you have done a good job.
Yeah, do we have any more input from the audience? Well, it doesn't look like. Thank you very much all for attending, and I wish you a very good evening.